Rockets are remarkable machines designed to propel objects, usually spacecraft, into space or through Earth's atmosphere. They operate based on a combination of physics principles, primarily Newton's third law of motion. For every action, there is an equal and opposite reaction. This means that by expelling gas or some other material out of the back at high speed, the rocket generates thrust that pushes it forward. Basic components of a rocket. Propellant. This is the fuel and oxidizer combination that, when burned, provides the energy to propel the rocket. The propellant can either be in solid, liquid, or hybrid form. It produces a vast amount of exhaust gases when combusted. Fuel, the material that burns, e.g., kerosene, liquid hydrogen. Oxidizer. Since rockets operate in space where there's no oxygen, they carry their own oxidizer, e.g., liquid oxygen. Combustion chamber. This is the part of the rocket where the fuel and oxidizer are combined and ignited. The combustion produces high temperature and high pressure gases. Nozzle. The nozzle is crucial to rocket propulsion. It accelerates the exhaust gases created in the combustion chamber to very high speeds. The nozzle is shaped in a way that converts the high-pressure, slow-moving gases into a fast-moving jet of gas, increasing the rocket's speed through thrust. Payload. The part of the rocket that carries the mission objective. This could be a satellite, astronauts, or scientific instruments. It is often located at the top of the rocket. Guidance and control systems. Rockets need to be steered and stabilized during flight to ensure they reach their destination. These systems include gyroscopes, accelerometers, and computers that control small thrusters or movable fins for course adjustments. Rocket stages. Large rockets often use multiple stages, each with its own engines and fuel. As each stage's fuel is exhausted, it is discarded to reduce weight, allowing the next stage to continue the journey. This process maximizes efficiency in space travel. How rocket propulsion works, the physics behind it. Rocket propulsion is the process of producing thrust by expelling mass, exhaust gases, at high speed. The working of rockets can be explained by two key physical principles. Newton's third law of motion. The law states, for every action, there is an equal and opposite reaction. In rockets, the action is the expulsion of high-speed gases in one direction, downwards or backwards, and the reaction is the thrust that pushes the rocket in the opposite direction, upwards or forwards. Conservation of momentum. Momentum, which is the product of mass and velocity, must be conserved in a closed system. The rocket expels gas, mass, at high velocity in one direction, increasing the rocket's velocity in the opposite direction to conserve momentum. Steps in rocket propulsion. Ignition. The rocket engines ignite the propellant, fuel plus oxidizer, creating an explosive reaction inside the combustion chamber. This process produces a large volume of high-pressure, high-temperature gases. Exhaust ejection. These hot gases are expelled through the nozzle at extremely high speeds. As the gases shoot out, the rocket experiences an opposite force pushing it in the opposite direction. This is thrust. Thrust and lift off. As long as the thrust is greater than the force of gravity pulling the rocket back down, the rocket accelerates upward. Once it overcomes gravity, it will continue to increase speed, heading into space. Atmospheric exit. In space, the rocket no longer faces atmospheric drag, so propulsion is more efficient. Rockets are designed to work in the vacuum of space by carrying their own oxidizer. In the vacuum, the rocket can continue to expel gases and increase its velocity as long as it has fuel. Types of rocket engines. Solid propellant rockets. The fuel and oxidizer are mixed together into a solid substance. When ignited, the mixture burns from the inside out, generating thrust. Advantages. Simple design, can be stored for long periods, and reliable ignition. Disadvantages. Once ignited, they cannot be easily turned off or throttled. Liquid propellant rockets. The fuel and oxidizer are stored separately in liquid form and are mixed in the combustion chamber. The burning process can be controlled. Advantages: can be throttled, turned off, and restarted. Disadvantages: complex plumbing systems, cryogenic storage, for some fuels, and can be less stable. Hybrid rockets. These use a combination of a solid fuel and a liquid or gaseous oxidizer. This allows some control like liquid rockets while being simpler than liquid propulsion. Ion and electric propulsion, used in spacecraft. These systems are highly efficient but produce very little thrust. They work by accelerating ions or electrons using electric fields. While the thrust is small, it can be sustained for long periods, which is ideal for long-distance space travel. The challenges of rocket design. Rockets are complex machines that face a range of challenges. Weight. Every kilogram of fuel, payload, and structure must be carefully calculated. Since rockets must carry their own fuel, the more fuel you add, the heavier the rocket becomes, which in turn requires more fuel. Efficiency. Rockets need to maximize their efficiency to escape Earth's gravity. This involves optimizing fuel consumption, staging, and choosing the right materials. Aerodynamics and heat. During launch, a rocket must pass through the atmosphere at high speeds, facing air resistance and extreme heat. The shape of the rocket is designed to minimize drag, and special heat-resistant materials are used to protect it from friction and heat. Guidance and control. Rockets need precise control systems to navigate their way into orbit or deep space. Even a slight deviation in angle can cause the rocket to veer off course, wasting fuel or causing mission failure. Structural integrity. Rockets must be strong enough to withstand the immense forces of takeoff, including vibrations, gravitational forces, and internal pressures from the fuel combustion, while remaining as light as possible. Stages of a rocket's flight. Launch and lift-off. The rocket engines ignite, and thrust builds up until it exceeds the rocket's weight. The rocket begins its ascent, moving through the atmosphere at increasing speed. Max Q, maximum dynamic pressure. This is the point where the rocket experiences the maximum aerodynamic stress, which occurs when the rocket is moving fast but still within Earth's atmosphere. It's a critical phase in terms of structural integrity. Stage separation. For multi-stage rockets, once the lower stage has expended its fuel, it is jettisoned to reduce weight. The next stage ignites and continues the propulsion, and this process may repeat depending on the number of stages. Orbit insertion. Once in space, the final stage of the rocket adjusts its trajectory to place the payload into orbit. This is often achieved by firing small engines for precise control. Payload deployment. When the rocket reaches its target orbit, the payload, satellite, spacecraft, etc., is released. Deorbit or disposal. Some stages of the rocket may be designed to fall back to Earth and burn up in the atmosphere, while others may be designed to be reusable, like SpaceX's Falcon 9 first stage. Modern innovations in rocketry. Reusability. Reusable rockets like SpaceX's Falcon 9 are changing the industry by reducing costs. The first stage returns to Earth for refurbishment and reuse, drastically cutting expenses associated with space missions. Miniaturization. CubeSats and small launch vehicles are emerging as important tools for launching smaller, cheaper satellites into space. These can be used for research, communication, and even asteroid mining. Nuclear rockets. In the future, nuclear thermal rockets might allow spacecraft to travel farther and faster. These rockets would use nuclear reactions to heat a propellant, providing much higher efficiency than chemical rockets. Rockets are marvels of engineering, relying on precise physics and advanced materials to overcome Earth's gravity and explore space. Their working is based on fundamental principles of motion and energy, making them essential tools for modern space exploration and satellite deployment.